Well, good morning, everybody. Today we're going to do some real science, and I don't mean kindergarten science either. I'd like to try to calculate the Earth's circumference, its tilt, rotation, and day length. Today we're just going to talk about circumference and tilt. I intend to do very carefully the scientific method for this experiment. The steps used are those taught in university business statistics and in business research. Steps will be clearly outlined as we progress, so nobody's confused. It's continually reported on YouTube videos. I see it all the time. Curvature, circumference cannot be measured. Okay? The Earth is not rotating. There's no way. Nothing shows rotation. Just can't be. And then, of course, since it's not a sphere, they're always saying there's no tilt. And I'm going to prove that there is. So the purpose here is to check each one of these with observational data. Very easy to measure and calculate. And I want to show that all of these are intertwined with much of that data used in everyday reality. So first of all, in the scientific method, we have the hypotheses. First hypothesis is the status quo. Basically, Earth is essentially a sphere. Circumference, tilt, latitude can be calculated, and they are consistent with each other. The alternate hypothesis, often called H sub A, is that any inconsistencies in the data or the calculations will show that the Earth is not spherical. So the first thing I did is to collect data. And I wanted to use many different cities from all across the world in order to not make it a one data point experiment. The premise is to collect from 3 series of cities running in 3 different lines, as I'm going to show you here in a minute with this map. So when I did this, I chose cities from as far north as possible to as far south as possible. So when I talk about the data in this series, I'm going to refer to it as the North and South America data, the Europe and Africa, and then finally the Asia and Australia data. So first of all, we needed, of course, the city names, which I'll show you. Then I needed latitude and longitude, which I took from this website. And then I corroborated the latitude and longitude with several other websites just to make sure I had correct data. Here is the map that I used. This is from timeanddate.com. You can see here that I have one line of data running north and south here, starts up here at alert up in Canada, runs all the way down to the south tip of Chile. You can also see this data point over here, right there. I decided not to use that point, King Edward Point, because the data I was getting from that was not consistent with itself, just wasn't good data. So I chose another point on south tip of Chile. Then I have cities here in Europe and Africa. Starting up here with Longyearbyen, up here, Oslo, and so forth. Sorry, Dan, London was out of my line of cities. This M and N right here I added in because those are the two cities that Eratosthenes used when he did his calculations. So I just included those for continuity. Then over here is my Asia and Australia line, starting up in Russia and down to Hobart, Tasmania. I also added in down low, down here you can barely see it, the site in Australia, I mean Antarctica, sorry. So that's my data. The cities, like I said, I picked latitude and longitude. So far in my experiment data, I have city name, latitude, longitude. So then from timeanddate.com, I took data for sunrise, the local time, for day length in hours, for solar or high noon local time, and the solar noon angle from vertical, which is in degrees. So it's you have the vertical, and then this is the solar noon, its angle from vertical. Each of those then I calculated for spring equinox, summer solstice, autumn equinox, and winter solstice. This is what the data looked like when I put it in Excel. So here I have the city name, spring, summer, fall, winter, the latitude, longitude, sunrise for each of those four, day length, solar noon time, and the solar noon angle from vertical. Those are input data to my experiment. So from that data, I made 3 calculations. You can see here, solar noon angle from the horizontal. So I not only wanted the angle off the vertical, I wanted the angle from the horizon up. The second thing I calculated is the Earth's tilt. The one thing that you need to know about this calculation is that it doesn't work for the tropics where latitude is less than 23.5 degrees. And the reason for that is because in the solar noon angles are so close to 90 degrees that when you try to make this calculation, it just doesn't work. And then finally, my calculation, I did the circumference of the Earth, which is it's going to be very similar to what Eratosthenes did, except instead of using two cities, I used the city that I chose and the Tropic of Cancer or Tropic of Capricorn, respectively. So for calculated latitude, that was another thing. On the previous slide, you can see I calculated the solar noon angle from horizontal for spring and autumn equinox, and I can show you that. So you, the angle from horizontal, I only did the spring equinox and fall equinox, and the reason for that will be clear in a minute. Each of those two values are exactly equal to the city's latitude. So all I've done so far is taken the angle from the horizontal of high noon at the equinoxes, and both of those numbers are equal every time to the latitude. And again, I can show you that right here, 40.7, 40.5, and New York is at 40.7. So we're within 0.2 degrees. Also make note that the star Polaris, which everybody knows as the pole star, North Star, the angle of Polaris from the horizon in the night sky only in the northern hemisphere is also equal to your latitude. That's always the case every night, and it's never, Polaris is never visible in the southern hemisphere. You should make note of that because, again, if the Earth were flat, we should be able to see it from, at least cities that are close to the equator, but you can't. The Earth's tilt. This is a very simple calculation. All we have to do is average the solar noon angle from the vertical on summer solstice with the solar noon angle from vertical on the winter solstice. So, piece of cake calculation, you all know, I added the two numbers divided by 2, and this gives me the tilt. And we'll see in a minute that tilt is equal every time to the accepted value of 23.5. Every single city that I used. When the tilt is negative, that means that the city is in the southern hemisphere. So, and the last thing, this is going to be a little more complicated to get, as Eratosthenes did, but it's still doable with just basic math. So no fancy hand waving here. So you'll remember, if we look back at Eratosthenes, he took solar noon data for Aswan. Aswan turns out to be exactly on the Tropic of Cancer. He used a stick and a shadow to calculate the angle from vertical of the solar noon for Alexandria. So Aswan solar noon was basically 90 degrees. So the sun at solar noon for Alexandria is going to be exactly 0 degrees. Then he was in Alexandria, so he used a stick that he had known length. He used the shadow, which turned out to be like 7.2 degrees off of vertical. And then he used a very simple ratio, the ratio of the number of degrees in a circle, 360 degrees. It's proportional to the difference in the shadow angle that we just looked at. And that number is equal to the circumference related to the distance from Alexandria to Aswan. Then we solve for circumference. Make a note that this distance from Alexandria to Aswan is actually the same as the distance from Alexandria to the Tropic of Cancer. So here is the next part of the circumference calculation. We have our 4 numbers and the ratios of those numbers. So in the northern hemisphere, I'm going to use the Tropic of Cancer at summer solstice, and then in the southern hemisphere we have to use the Tropic of Capricorn at winter solstice. And I'm doing that instead of using the 2 cities as Eratosthenes did. For distance between the city and the distance to respective tropic, I'm using the latitude of the city minus 23.5 degrees, which gives you in degrees the angular distance between the given city and the Tropic of Cancer, or the Tropic of Capricorn. You take that number in degrees and multiply it by 69 miles per degree, which you can look up anywhere and it will tell you that number. Notice that this is miles per degree. When I multiply times degrees, I get miles. So the number of miles between the city and the tropic, and we'll call that D sub C. So then I skipped one. We have the 360 degrees divided by the solar noon angle from horizontal. So this is degrees and degrees. When we divide those two, I'll call that A sub C, and it's a dimensionless number. So then we get down to calculating the circumference. It's very simple now. We just take A sub c and multiply times D sub c. This is the pole-to-pole, this way, circumference, also called the meridional circumference. The accepted value here is 24,860 miles. Again, you can look that up anywhere. You'll always get that number. This is the summary of my results. You can see here, this is my North America, South America numbers or cities. This is my Europe and Africa cities. I added, you remember I added in Eratosthenes, 2 cities. And then lastly is the Asia, Australia cities with the McMurdo station added for Antarctica. So again, these are the latitude, longitude that we looked up for each city. This is the Earth's tilt that we calculated. I showed you the calculation, and you can see clearly that it's 23.5, 23.4 all the way down. And you remember that I said the negative numbers are in the southern hemisphere. And you can see that as well. The circumference that I calculated, once again, these numbers are all very, very close to the accepted value, 24,860 miles. I don't see how you can not see that these numbers are consistent with each other. And then, of course, the last thing was a very simple calculation of the latitude. So I actually calculate the latitude, whereas I looked it up over here. And you can see that these two numbers are exactly equal all the way down for each of the 19 cities. So those are the results of my experiment. Now we're going to analyze those results to see what we think. Again, calculation of latitude. I used only solar noon data. Shows that the sun appears in the sky exactly as expected by spherical data, not just once, but twice during the year on the equinoxes. This works for all 19 cities from every place on the sphere. Calculation of tilt gives the value as expected only using solar noon data for the solstices. Circumference we calculated using solar noon angles at the solstice and the distance from the respective tropic, which again gives us identical values for every city. So you can see that no matter where on Earth you are, you're getting the exact same number for circumference. I know that all you flat Earth guys and girls will be glad to know that there are some errors. There's always some measurement error in statistical analysis. You just, if they were exactly identical, you know, to the decimal place, it would be very suspicious looking data. You cannot expect observational data to produce those identical results. In my analysis, there's no error greater than about 1%, which is just remarkable. And again, from before, you remember that I did exclude some data in calculating tilt, which was recommended by the website, because solar noon angles will almost be 90 degrees and difficult to get an accurate measurement. And then from Eratosthenes, the city of Aswan was eliminated because the angular distance, or the angular distance of the sun from vertical is less than 1 degree. It was like 0.2 degrees, and you just can't calculate with that small of a number. So my conclusion, again, it's very clear from this data and calculations from 19 cities. I didn't use just one point. I did repeated measures. So 19 cities from around the world. We have to reject the hypothesis H sub A, and that the Earth cannot be a sphere. So we reject the alternate hypothesis. Normally, in statistical analysis, we would say we failed to reject the null hypothesis, and you can look up reasons for that. However, in this case, there's no probabilistic nature to the data. Therefore, we accept H naught, and the Earth is a sphere. No question. The data shows the Earth is a sphere. For further study, I'm hoping to do more videos. I'm going to use the same data that we saw in this video, using this same data, distances between cities. We will prove rotation, and we'll be able to compare flat Earth distances to spherical Earth distances. In part 3, using the same data, I want to look at the length of the day over the different times of the year. And then part 4, I've been dying to do this video on using winds and storms like hurricanes and tornadoes, and we'll see some fascinating information there. So I look forward to seeing you in further videos. Here are the websites that I used for all of the data and the calculations that I got. I'll try to post these in the comment section if you want to look out there. My next acknowledgements are for GlobeSite channels that I encourage you to look at. Simon Dan, of course, is my mentor. He encourages me all the time. His channel is full of good, verifiable information, and it's very entertaining. You'll really enjoy it. Be sure to catch his astronomy lecture series. There's a series of 5 lectures that you'll really enjoy. Conspiracy Cats and his twin brother Baldy Cats. I'm telling you, this guy really knows his physics, and he can out-calculate anybody. Anti-Flatter, he's kind of new, and I think he's stupendous, and he's really got some hilarious videos, but he's always right on the money. Wade's Underworld gives us some great observations from down under. And then finally Rapidex, my buddy, he makes some terrific original music videos. So if you don't go watch these guys, shame on you. And that's the end of my video for today.